Look out over any modern cargo port, and you see pure, standardized order. Millions of identical steel boxes, stacked high, moving efficiently worldwide. Before standardization, loading a ship was a slow, manual struggle. Dock workers spent days hauling loose sacks and crates into the unpredictable holds of cargo ships. We solved that chaos by using a rugged steel shell. But that ruggedness is deceptive. Inside, a container is a surprisingly fragile environment. The walls and roof are merely protective panels. They provide zero structural support for the weight of the cargo. When a ship pitches and rolls across the ocean, it generates immense kinetic energy. If the interior isn't packed to account for these forces, the movement of the cargo can easily tear the metal box apart from the inside out. Behind the standardized shape, the system relies on heavy-duty engineering and unforgiving physical rules. This diagram shows the container's true structural skeleton. The entire weight of the box and its cargo is carried solely by these heavy corner posts and the crossmembers hidden underneath the floorboard. Because of this design, the first rule of packing is dictated by gravity. Cargo weight must be evenly spread over the largest possible floor area to engage as many of those bottom crossmembers as possible. There are strict mathematical limits to this distribution. A critical rule mandates that no more than 60% of the total cargo weight can sit within half the length of the container. Exceeding this point loading limit concentrates too much stress on a single section of the frame. The center of gravity must also sit as low as possible and stay perfectly centered. Stacking the heaviest items high or off to one side makes the entire unit prone to tipping during a highway turn or rolling sea swell. To counter the kinetic forces of a moving vessel, everything inside must be locked in place. Packers use internal lashing rings built into the rails, along with wooden dunnage, heavy timber blocks, and tight cross-bracing to ensure the cargo cannot shift. Strict adherence to these rules of gravity and force provides the stability a thin metal shell needs to survive the open sea. Of course, global trade involves items that ignore these standard constraints. Whether it is massive turbines, luxury ocean yachts, or oversized steel pipes, they frequently exceed the physical dimensions and weight limits of a closed box. To handle this project cargo, the container design adapts. Open-top containers solve the vertical height constraint by removing the solid roof, allowing heavy machinery to be lowered straight down by a crane. For truly massive loads, flat racks and platform containers discard the side and roof walls. By relying on flush folding ends and reinforced bases, these units can carry concentrated payloads of up to 45 metric tons. Even when stripped down to a bare base, the underlying isoframe remains the same. The physics of how they lift and stack stay consistent, allowing them to plug right into the global logistics system. The physics get more complicated when we introduce fluid dynamics. Using large internal bladders called flexi-tanks, shippers convert a standard dry container into a bulk vessel capable of holding 26,000 liters of liquid. Transporting that much liquid creates intense, dynamic sloshing forces that constantly push back and forth against the closed container doors. To counteract this energy, the inner walls are lined with heavy corrugated cardboard and reinforced with steel bulkhead bars at the entrance. Then we have thermodynamics. Refrigerated containers, or reefers, handle the exact opposite of inert cargo. They transport live, respiring commodities like fresh fruit, which continue to consume oxygen and release heat long after harvest. While frozen meat is packed in a dense, solid block to keep the cold in, live fruit requires specific ventilation spacing. Without room for the cargo to breathe, it will quickly suffocate and rot. This diagram demonstrates the air circulation inside. Chilled air is forced upward from a T-bar floor, pushing through the cargo to remove heat and gas. To ensure the air can return to the refrigeration unit, the cargo must stay below a specific red line marked on the upper walls. Managing fluid dynamics and thermodynamics turns the interior into a dynamic environment capable of sustaining life across thousands of miles. A loaded shipping container meeting a truck chassis represents the final, seamless step of a journey defined by absolute precision. Global trade functions through millions of these individual physics equations, each one solved to keep the cargo from destroying the carrier. Behind every door is a custom-tailored physical environment, whether it's pressurized by a Flex-A-Tank of juice or ventilated for a cargo of breathing apples. This exoskeleton choreographs a hidden ballet of physics, allowing a single, unified infrastructure to handle the world's most sensitive and massive goods.